good evening and welcome to the Mathematics News. It's cold, it's Tuesday, it's time to do some maths. Okay, so it's time for the second part of the work, energy and power topic. This chapter really stands apart from the rest of the syllabus for M1. It deals with energy, and it mostly deals with situations where you don't have to worry about constant acceleration. They're really easy to spot in the exam because they involve energy. They talk about work done, kinetic energy, potential energy, resistance, things involving energy. When they ask you something involving energy, you know it's going to be involving the formulas that we've talked about so far. The first formula is to do with work done, and work done is the force involved multiplied by the displacement. Sometimes if you're talking about something that is just traveling along a horizontal road, then it translates into the difference between the kinetic energy at the end and the kinetic energy at the beginning. So sometimes it can be considered simply as just being half mv squared minus half mu squared. And that's just if you're talking about the force of the engine, the driving force, that's how fast it's going at the end, that's how fast it's going at the beginning, the v and the u, and then you can work out how much kinetic energy is happening at the end of the journey, take away the kinetic energy at the beginning of the journey, and that tells you the change in kinetic energy, which translates to the work done. But that's only really if you're talking about something going horizontally. You do have to consider things that are going up and down as well. And so as soon as you have something that's falling or something that's going up or down a slope, we have to consider potential energy as well. But we've got this basic formula for kinetic energy, which is half mv squared. The formula for potential energy is mgh, where m is the mass of the object, g is the acceleration due to gravity, 10 for all our purposes, and h is the height above the ground. So on a very simple example here, we've got 4 kilograms, which is 3 meters above the ground, and if you were to drop that box, it would sort of accelerate and then hit the ground, and it would increase speed. So if it started with a velocity of nothing, then you can work out the amount of potential energy it's got. It might have kinetic energy, but let's just say it's got no kinetic energy, and you drop it and it falls to the ground. At the beginning, it's got potential energy, the energy which will make it fall, and that could be found by using mgh. So in this case, it would be m4 times g, which is always 10, and the height it's falling is 3 meters. So that would just be 120 joules. That means that there is 120 joules worth of energy that will make this fall. And as that falls, by the time it gets to the bottom, the potential energy will have gone. It starts with potential and no kinetic. By the time it's just about to hit the ground, it's got no potential, but it's picked up some kinetic. And the whole thing will be conserved. So at the beginning, it's got 120 joules. At the end, it'll have 120 joules. But the energy will transfer from being potential to kinetic. So at the bottom, that 120 will equal a half mv squared, and then you can work out how fast it's going. That must mean, if there's a 4 kilogram box, that's the same as having a half times 4, so that's 2v squared, and that equals 120. So v squared must be 60, and the speed it's going is 60 square rooted, which is about 7.75. So 7.75 meters per second. And there's a basic idea here is that overall the energy doesn't disappear anywhere. There's no resistance here, it's just falling through the sky. There's no driving force, there's no engine, and we have some potential energy at the top of the drop. We have some kinetic energy at the bottom of the drop, but they are the same amount of energy in total. The energy at the beginning is equal to the energy at the end. And the only reason why it wouldn't be different is if you had an engine or if you had resistance. Let's imagine a similar situation. It doesn't matter if it's sloping down like this. If we ignore resistance and there's no driving forces involved, the sort of calculations involving a slope like this would be exactly the same. This has, it's 4 meters above the ground. The potential energy here would be calculated in just the same way. These two situations, the potential energy is the same. This has 4 meters above the ground, so the potential energy is m7 times 10 times the height above the ground, which is 4. So it's the perpendicular height above the ground. So that would be 280 joules. And in a similar way to this, you could work out the speed at the bottom. The only difference would be if you had some resistance, and so some of the resistance would take away from the speed at the end. But you can calculate the energy at the beginning, you can have work done by a driving force, you can take away the resistance, the work done by resistance, and you're left with the energy at the end. And this is exactly the same principle that we talked about in the last video. It's just now we have kinetic and potential mixed in. Let's have a look at a couple of questions. So, on this side I've got, and this is a real situation based on what happened this morning. There was a penguin on top of a cliff and I pushed him off the cliff because I hate penguins. I hate them penguins. But imagine, right, this penguin has the potential to fall. So it's got some energy at the top of the cliff. And right at the top, it has potential and no kinetic because it's not moving. It would then fall, and at the bottom, by the time it gets to the bottom, the height is 0. So it's got no potential, but it will have picked up some kinetic energy because it's falling. So what we can do is we can work out exactly how much energy there is at the beginning and how much energy there is at the end, because the whole thing will be conserved. There'll be the same amount of energy overall. So at the top, the kinetic energy is 0 because it's not moving until I push it. The potential energy is equal to mgh, which this is a 30 kilogram penguin, always times 10, and the height, which is 250. So that gives me 300 times 250. So the amount of energy at the beginning of this journey, this tragic journey, is, what's that, 75,000 joules. At the end of the journey, there'll be no potential, but there will be kinetic. So the kinetic energy will be half times m, which is 30, times v squared, and the potential is nothing. Because it's fallen all the way down at 0, the height is 0, so it's m times g times 0. But we know that energy is conserved overall, so this has to equal this. So that means that v squared can be calculated. We can just divide this number by 15 and then square root it. So that means the velocity of the penguin as it hits the ground is 70.7. That's pretty fast for a penguin. But he was fine. He was fine. I pushed him off the cliff, but he was absolutely fine. There was a big cushion there. He was fine until I ran him over later. Let's just move on to another question. Okay, now this is beginning to look a bit more like an exam question. What you often have is something going up a slope or down a slope, something that is moving, and you have some energy at the beginning, you have some energy at the end, and you have a driving force pushing the object forward, usually a car or a lorry, and then you also have some resistance. And there's going to be something missing in this. You might be missing the velocity at the end, you might be missing the velocity at the beginning, you might be missing the mass of the object, or you might be missing something involving the forces. You might be asked for the work done by the driving force, you might be asked for the work done by resistance. Something will be missing, but you'll have all the information you need in the question to find that missing number. Here I've got the mass of the car. Let's say this is a car going up a hill. It starts with 11 meters per second. It finishes with 8, so it's slowed down a bit. But the engine is pushing it forward. There's resistance pulling it back. But overall, it gets to the top of this hill, and so it gains potential energy the whole time. It starts with kinetic and no potential. It finishes with some kinetic, a little bit less, but also it's gained potential because it's gone up the hill. So we really need to know that height. So if they don't give it to you straight away, if you have something involving the distance along here, so it's gone 70 meters along this triangle, the angle is 4, we can work out the height. So you need to know the height, unless you know everything else and the height is what you're looking for. That happens sometimes. But just using trigonometry, we can work out the height of that would be 70 sine 4 degrees. These questions often have a very small number here. Presuming this is a right angle triangle. Okay, so let's go through this slowly. We say at the start, what have we got? We've got kinetic energy, and that is a half mv squared. So it's a half times 1,500 times the velocity at the beginning, which is 11 squared. Okay, there is no potential energy at the bottom of the hill, there is nothing. Then we have the work done by the driving force. Let's call that WDD, and that is going to be the size of that force multiplied by the distance travelled. But actually, in this question, you're just asked for whatever the work done is. We don't actually need to know the size of the force, but if you knew the work done, you could easily divide it by the distance travelled and then find the actual size of the force. But we just need to know what that missing quantity is. We're going to take away the work done by resistance. There's a resistance here of 60, and the work done formula for anything is always the force times the displacement. So here we've got the 60 times by the distance over that hill, which is 70 meters. And at the end, we still have some kinetic, which is 1/2 times 1,500 times 8 squared. And we have potential now because it's gone uphill. Potential is m times g times h. So it's 1,500 times g, which is 10, times the height of that hill, which is 70 sine 4. It's from here that we can actually piece together an equation. Let's just move this over. So our equation is looking like this. We've got this number for the beginning, which I haven't worked out yet, 0.5 times 1,500 times 11 squared. So we start with 90,750 joules, plus the work done by the driving force, which we're looking for. Take away the work done by resistance, so that's 60 times 70, that's 4,200, and that equals the total energy right at the end, which is the kinetic plus the potential because it's gone uphill. 0.5 times 1,500 times 8 squared, which is 48,000, plus this horrible number here, 1500 times 10 times 70 sine 4 degrees, which is 73244.29743. As always, I'm being as accurate as I can now, but I'll round it right at the end. So these two together, plus the work done by the resistance, take away the energy at the beginning, will leave me with the work done. And I'm missing here, but you could have been missing one of these items, but you can piece them all. You can piece everything together with this simple idea: is what you've got at the beginning, plus the work done by the driving force, take away the work done by resistance, equals the energy at the end. So let's work it out. So it's this plus the 48,000 plus the work done by resistance minus the energy at the end, and that gives me the work done by the driving force would be 34700 joules to 3 SF. Okay, and from there, if they did ask you, you could work out the size of the driving force, because the work done is equal to the size of the force times the displacement, which is 70 in this case. So the force of the engine here is 496 newtons to 3 SF. That isn't what they're asking here, but you could easily be asked that as like a second part of a question. This system is foolproof. All we need to do now is sort of move on to the next bit eventually, which involves power, but we'll do that, I think, on Thursday and Friday. This is going to take us a while to finish the work I need you to do. So overall, really, before Thursday, I want you to aim to do exercise 9A and exercise 9B. But 9A, you just have to do maybe the first 7 questions. And 9B, I want you to try and do the beginning, so questions 1 to 6, to get used to the idea of potential energy, but then do the exam questions afterwards, so 15 to 19. And I've got the solutions, and I'll put those in my email and on the homework. Good luck. From the Mathematics News Desk, good evening.